Hello everyone, how's it going? Welcome back to my YouTube channel, and in today's episode, let's explore how to fine-tune your large language model using ORPO, which is a very interesting technique that combines both supervised fine-tuning and also DPO. When we traditionally fine-tune a large language model, we take a base model, and then with an instruction answers dataset, we perform supervised fine-tuning. But then, after we fine-tune the model with this technique, we proceed to perform DPO to align the answers with our preferences. So you can see here that traditionally we do two techniques to fine-tune the large language model. But if we do ORPO directly, we can combine or merge these two steps into one, and we can have our answers aligned to our preferences. And let me show you how to do it now. So first, let's install all the libraries that we will be using for this video tutorial. We will be using Unsloth to fine-tune the LLM because it allows to fine-tune the model 2 times faster than if we just purely use Hugging Face. Let's also install transformers, 𝗀𝗶𝗸𝗲𝗃, accelerating bits and bytes, and also WMB to do model experimentation and save our metrics. Then let's import all the libraries. Since we will do model experimentation and save our metrics in WMB, let's load the credentials. So in my secrets, I have here my WMB API key. So you need to click on notebook access, and then you can proceed to load and log into your WMB account. And now let's proceed to download the model and the tokenizer. So let's do model and tokenizer equal to fast language model from pre-train, and here let's specify the model name. In this case, we'll be using Llama3 8 billion parameter model. So this model we will fine-tuning using ORPO. Also, let's specify the max sequence length of the model. In this case, Llama3 has 8,000 tokens, so let's use 8,192. And then let's also specify the data type. In this case, since we're using a VM T4, let's specify none, but this will end up choosing float 16 as a data type. And also let's load our parameters of the model in 4-bit. In the quantization will be 4-bit, so let's do true here. If you're enjoying the content so far, don't forget to subscribe to the channel because it helps me. If you're enjoying this content so far, don't forget to subscribe to the channel by clicking on this button because it helps me to create more content. Also, smash the like button below and turn on the notification bell so you never miss a new video. And now, while this is being downloaded, let's proceed to specify the LoRA adapters that we want to use in our model. So let's do model equal to, also using again fast language model, but in this case let's specify get PEFT models. Well, here we'll specify the matrices that we want to fine-tune. Let's specify here the model, which is the Llama3. Also let's specify R, which in this case will be 16, and also let's specify LoRA alpha, which is another parameter. Usually it's recommended to use R times 2, so let's do 32 for alpha. Now let's specify the matrices that we want to fine-tune. So let's do target modules, and in this case let's specify these ones that I already have here. You can specify as many as you want, considering that the more matrices that you fine-tune, the more time it will take to fine-tune the model. Then let's add more parameters. Here we'll specify a dropout of 0, because when we read the documentation of Unsloth, they mention that 0 is optimized, also bias equal none, gradient checkpointing equal to Unsloth, the random state for reproducibility of these experiments. Also, when we work with Unsloth, they have a parameter that allows to do a rank stabilized LoRA, but in this case let's assign it as false to perform the fine-tuning faster. And also this LoRA configuration, when we quantize the model parameters, let's use it also as none, so we don't initialize it. And then let's check the amount of parameters that we will be fine-tuning. So let's do print trainable parameters. So we see here the amount of parameters that the model has. So here we see the 8 billion, and we see that we will be just fine-tuning 0.51%, which is just 41 million parameters that we will be fine-tuning. Now let's proceed to load our dataset. So let's do dataset equal load dataset. I already selected the dataset that we will be working on. Let's download the data, and in the meantime I'm gonna show you how the data looks like. It has 4 columns, an instruction, an input question, and then here we have 2 answers, an accepted answer and a rejected one. When we fine-tune using ORPO, we are aligning the responses of the model to our preferences. So we feed 2 responses, one that we accept and we agree on based on this question, and one that we reject. So the model will be learning and will be given more points, let's say, to the accepted answers to the rejected ones. Here we see that the instruction is, you're an AI assistant, you will be given a task, and you must generate a detailed and long answer. Here we have the input question. Here we have a response that we agree on based on this question. So probably the result of this question is correct here, and here will be incorrect. It's important to consider that the responses for this dataset were generated using large language models. For the accepted column, it was generated using GPT-4, and for the rejected was using Mistral. And now that we have an idea on how our dataset looks like, let's proceed to format our prompt. Here that we have our data already downloaded, let's load our prompt. We'll be using Alpaca. Here we specify as a prompt the instruction and also the input. As a chosen, we will be using the accepted response, and then we specify end of sequence token, so the model knows that it should stop generating the response there, and also the rejected, which will be the rejected answer plus the end of sequence token. So then let's create this function with the Alpaca prompt, and then let's apply it. So let's use dataset equal to dataset.map, and here we can use the function that we just created. Let's apply this Alpaca prompt to our dataset, and let's print it out so you can see how it looks like. Here we see that in the first row we have the instruction. We see that below is an instruction that describes a task paired with an input that provides further context. Write a response that appropriately completes the request. Here we have the instruction. You are an AI assistant that helps people find information. And then here we find the input question. Here we have the response, the accepted one, and then here we have the rejected response. And now let's split our dataset. So let's do train dataset equal to dataset. Here let's specify shuffle, so we can shuffle our rows, seed equal 10. And then let's pick just 3000 rows out of those 16K that we have. Preferably when you are fine-tuning your large language model, you want to select as much as possible, but in this case, just to fine-tune the model faster, let's just pick 3K rows. And for the evaluation set, let's do the same, but let's specify less rows. Let's just pick 1000 rows. And now let's proceed to load the arguments of ORPO. And in this case, let's set here 8192, which was the max token that we specified earlier for Llama3. Also some parameters to optimize the process. We will be logging every step one by one. We will use Adam as an optimizer. Let's assume that our learning rate scalar type will be linear. Let's specify more steps. Let's specify that we want to have 20 steps, and let's save the results in the folder outputs and the metrics in WMB. Then let's proceed to create our ORPO trainer. So let's do ORPO trainer equal to ORPO trainer. Here let's specify the model. So it will be model equal model. Also the tokenizer. Let's specify our train dataset. So we also call it train dataset. And our evaluation dataset, let's specify it here. And now let's specify our ORPO arguments. And then let's run this. Since I'm using FreeCodeLab, let's change the max steps from 20 to 10, because sometimes I'm out of CUDA memory. And now let's fine-tune the large language model using ORPO. So let's do ORPO trainer.train. And then let's see how fast this goes. So we will have 10 steps and we'll be logging our metrics on each step. Let's see how fast it goes. We will be fine-tuning 41 million parameters, 10 steps. Let's see how it goes. Here we can see the results of the fine-tuned large language model. It took less than 3 minutes for 10 steps, and we can see that the training loss goes down, which is amazing. Now let's proceed to do inference from our large language model. We'll be given an instruction, and then let's ask this question. So the instruction will be that you are an AI assistant, you will be given a task and you need to perform the task thinking step by step and needs to justify the steps. And the question will be, well, a mathematical question. It will be to solve this equation. Let's see the response of the large language model. In this case, we are using continuous inference, so the response is printed right away as it's generated. Amazing, we can see that the answer is correct. Now let's ask a different question. Let's go now with this question that I have here, so we can see that it works for other purposes and other topics. Describe the steps to take when preparing for a job interview. Let's see if the model gives a correct response, but also thinking step by step. Let's see this one now. Let's see here. Research the company and the position you're applying for. Prepare a list of questions to ask during the interview. Practice answering of common interview questions, and so on. So as you can see, after fine-tuning the large language model using ORPO, it's working as expected. And that was it for today. Now you know how to fine-tune your large language model using ORPO. I hope you find this video tutorial very helpful, and if you have any type of questions, please leave them in the comment section below. I'm gonna keep uploading more videos, so please subscribe to the channel, hit the like button below, and don't forget to turn on the notification bell so you're the first one to know when I upload a new video. See you next week.